thank you for the introduction and thank you for inviting me to this conference. It's a really nice event, and hopefully I'll be able to attend it next time. And today I will show you some results of our theoretical work related to precision metrology. However, before I move on to calculations themselves, I would like to give you one or two or maybe 3 slides of introduction into the experimental work that's being done and how it relates to what we do. Because without this introduction into the experiments, my talk would be extremely chaotic and random. So let me begin by familiarizing you with some devices and experimental stuff. So first of all, if you ever wonder how you measure pressure of a gas, it turns out it's not that trivial. You need a quite fancy device. The most common devices of the type are based on piston cylinder scheme or system. As you can see on the plot, the idea is very simple. You have a pressure balance, and there are 2 forces essentially, the gravitational force and the force from the gas pressure acting in the opposite direction. So the idea is very simple. Of course, the difficult thing about this device is to measure this effective area that essentially touches the gas, and also the coefficient which describes the expansion of the device as you increase the pressure. And to find this coefficients and this parameters for a given apparatus, you need to perform quite substantial calibration. And for this calibration, you use nowadays different techniques, which 2 of them I will introduce to you in a second. So the first technique, which is used for calibration, is called the electric constant gas thermometry, or DCGT. The idea is that you measure, you have 2 capacitors embedded in a large copper block. And these capacitors are identical, but one of them is filled with gas, with the working gas, and one is under vacuum. And what you measure is you measure differences in capacity between these 2 capacitors. So this is the capacity of the capacitor filled with gas, and this is the empty one. And you can show from basics electrodynamics that this difference, this relative difference in capacity, is related to the dielectric constant of the gas, which is this epsilon r. And you also have some effective compressibility of the capacitor, which describes the fact that if you increase the pressure, the capacitor itself ever so slightly expands. But this effect is very small, and you just measure it for a given device. So this is effectively empirical parameter which you have to measure. But the most important thing is this dielectric constant. I don't write it explicitly here, but it depends on pressure of the gas. This is the electric constant. And what's the theory behind that? So how we can get from the measurement of the capacity, how we can get pressure of the gas all of a sudden. And this is, of course, not trivial, but you need to use 2 fundamental equations. The first is the Clausius-Mossotti equation, and it relates the electric constant to gas density. So you can see on the left we have the electric constant in this weird combination, and on the right you have gas density, this rho, and then you have these coefficients which are called the electric virial coefficients. And the second equation you need is just the equation of state, and it relates pressure to the density, and this virial coefficients you have are called density virial coefficients. So you combine these 2 equations to eliminate the density, basically. You want to eliminate, eliminate the gas density. You combine both of them. And what you get when you do that is an equation which is like a working equation of this DCGT, which expresses pressure as a form of just infinite sum over this parameter xi, which is just dependent on the capacity, on the measured capacity, and the coefficients, this g, they include all the rest of the stuff. So all these dielectric coefficients and virial coefficients are embedded in this g factor. So then if you measure capacity, you measure this xi, and once you have measured it, if you know the coefficients, you can evaluate the gas pressure directly. So this is the main idea here. So you measure xi, then if you know the coefficients, you can evaluate the pressure. The second technique I would like to show you is a bit similar, but based on on measurement of a different phenomenon. So now the second experimental technique is called the refractive index gas thermometry. And here you have a cavity, spherical cavity, it's like spherical shell, and the whole stuff is filled with working gas. And what you measure here is you measure resonance frequency of this cavity. So each cavity has certain resonance frequency, and you measure change in this resonance frequency as you increase the pressure. So you measure effectively this Fm as a function of pressure, and it's related to the N, which is the refractive index of a gas. So if you know the refractive index, you can find this shift in the frequency or vice versa. And here, instead of this Clausius-Mossotti equation, which used the electric constants, the electric coefficient, here we use Lorentz formula, which expresses this fundamental property, refractive index, as a function of density of the gas. And these coefficients, which are different in general, are called refractive virial coefficients. So you have three types of coefficients. You have the electric virial, density virial coefficients, and refractive virial coefficients. Something is not working. Oh, it's working. So the first issue you have to deal with is choice of the working gas. So you have to fill this device with some gas. And of course, you want to have a gas which is completely unreactive, which is stable and available in large quantities. So for that, you would need helium, neon, and argon would be a good choice. So basically noble gases, maybe N2. The second thing is that you want to evaluate all these virial coefficients. It would be best to take them from theory. So you need high quality theoretical predictions. And for that, of course, helium is the best because it's the smallest possible system. And the second requirement, or the third requirement, would be that this the system, this working gas, has large polarizability, because then your sensitivity to impurities is low, and then that's why argon or neon are much better than helium. Helium is very difficult to polarize. Neon and argon are better, and N2 is even better. So what's the state of the art now for both these techniques? You use helium as a primary pressure standard. And the uncertainty you can get is about 2 parts per million in the pressure measurement. Devices based on argon and neon are close seconds, with uncertainty several times larger, and work on N2 is ongoing. I will circle back to that in the end of my presentation. Okay, and now slightly moving towards the theoretical bits. So first of all, it's important to point out that in recent years, we had a bit of a paradigm shift in all this field of metrology, because historically, this type of measurements I have mentioned were performed at different pressures, and then by inverting these equations, you can generate these virial coefficients, or the electric virial coefficients, or density virial coefficients. So these measurements historically were used to find these fundamental properties of a gas and to find the equation of state of the gas. In recent years, theory improved to a degree which enables first principle calculation of this dielectric coefficients or virial coefficients, and then you don't have to measure them anymore. You can just measure the capacity and directly generate what's the gas pressure. You can find by just one measurement, you can find the pressure of a gas. So then what do we need from theory to calculate all these coefficients which are needed? So for density virial coefficients, so these were the coefficients in the standard equation of state, virial equation of state. We need, for second virial coefficient, we need two-body interaction potentials. For the free body interaction, for the third virial coefficients, we need three-body interaction potentials. So if you restrict ourselves to helium, for the second virial coefficients, we need interaction potential for pair of helium atoms, so two helium atoms interacting. For third virial coefficient, we need a potential for interaction of three helium atoms simultaneously. And if you can continue, of course, 4 or 5, but the effect is smaller and smaller. Then for dielectric virial coefficients, so these coefficients which appear in the Clausius-Mossotti equation, so these are these guys. You need, for the first coefficient, you need polarizability. For the second, you need collision-induced two-body polarizability. So essentially polarizability of two helium atoms together, which is because they're interacting. The polarizability of two atoms is not the same as of two atoms separately, right? There is some change in the polarizability due to the interaction. And the same for the third coefficient, you need collision-induced three-body polarizability. So change in the polarizability due to the fact that we have simultaneous interactions of three helium atoms kept together. And for the refractive virial coefficients, so for the virial coefficients which appear in the Lorentz formula, so this refractive index, refractive coefficients, you also need the same data as above, but you also need magnetic susceptibility of this atom. And one thing to mention, I have to mention here, is all these coefficients depend also on the frequency of the laser that you use for the measurement. So additionally, all these coefficients, I don't write it explicitly, but they also depend on the frequency at which you perform the measurement. In the case of this first experimental technique, so the DCGT, there's essentially a static field, so the frequency is 0, but in case of the other one, you perform measurements at some finite frequency, and you have to have all the data for this frequency. So implicitly, everything depends on frequency too. So let me start with helium, which is gas used for primary pressure standard. So first of all, we want to have this first coefficient, this I epsilon, and it's a very nice expression, very simple one. You have just some numerical factor multiplied by atomic polarizability and multiplied by Avogadro constant. Since 2019, Avogadro constant is just a number fixed forever. You no longer measure it. It's just a constant of nature. So we don't have to worry about this. You just take it from the book. So pi is also known to sufficient accuracy. So what you need to have is just the atomic polarizability of a gas. And we use, in general, in all calculations I will show you, we use non-relativistic QED. So what we do is we perform expansion of any quantity you want to calculate in the powers of the fine structure constant. Please don't confuse this alpha with that alpha. And inverse nuclear to electron mass ratio. And in the case of helium, you can split the results into several contributions. The first is non-relativistic, which is of course the largest, and then you add relativistic corrections, relativistic recoil, QED corrections, QED recoiled, and you add corrections until you converge with sufficient accuracy. And then if you compare the best experimental result and the best theoretical result, you see that actually the theoretical data at the moment is more accurate by a factor of, I don't know, 20 or something. and it can be used for this measurement by just taking data from theory and using it in the measurements. But of course, this first coefficient is not everything. We need also this virial coefficients that we have to go through. And for that, to get the first density virial coefficient, we need two-body interaction potential. And in 2020, we developed new potential for helium pairs, so for helium-helium, which also includes many corrections beyond non-relativistic Born-Oppenheimer. And you can also see in this graph what's the progress in the accuracy of theory. So these color lines are theoretical. This is relative uncertainty in the second virial coefficient. So these color lines correspond to theoretical results from each year I show here. And you can see that the experimental data, which is in black dots, has been surpassed somewhere near, I don't know, 2012 by theory. And now we have a substantial improvement in theory, so that, again, we can just take this virial coefficient from theory. The next stuff is the third density virial. And for that, we need free body interaction potential. And the additional difficulty here is that to actually calculate the virial coefficient from the interaction potential, it's quite straightforward for two-body interaction. But if you have interaction of three bodies, then you need path integral Monte Carlo calculations. You can no longer do it sort of deterministically. And in last year, we developed a new potential for free body helium. And again, using this new potential, we are able to substantially improve the relative uncertainty in the third virial coefficient, and surpass the experimental data, which is also in black, and it's quite sparse and available only for several temperatures. Next, the next challenge was the electric virial coefficient. You need for free body polarizability for that. Last year, together with the potential, we developed also polarizability surface. And in this graph, you can see this blue line is essentially our result, and blue is shaded in blue is the uncertainty of our data. And the experimental results are scattered here, somewhere here. As you can see, these experimental results, which are very previously, were not very reliable. They had quite large error bars. And also, in our case, the uncertainty that we get is much, much lower. So again, experimentalists can just take this value and plug it into their device. Now I'll move to argon. As you can see from this equation, everything in the first coefficient depends on the polarizability. So if you have a larger polarizability than helium, then you're less sensitive to impurities, because the primary impurity that you have is water vapor. And water vapor has a very large polarizability. So if you have even a tiny amount of water in your helium gas, then it will greatly increase your error. But if you use argon, which is polarizability like 5 times larger, if I remember correctly, then your sensitivity to this level of impurities is much lower. So a natural choice was to use argon as a next working gas, or neon. We did both, actually. I show results for argon because experimentalists prefer it for some reason, but the same thing was done also for neon. So the first thing, again, is this essentially polarizability. Here, I explicitly want to write that all this depends on frequency. So you have polarizability at a certain frequency. So people call it dynamic polarizability or frequency-dependent polarizability. Of course, the first sort of realization is that it's impossible to reach the same accuracy in the polarizability for argon as for helium. This is simply not possible with theory that we have. But it's not the end of the day, because that's not the end of the world, because we have static polarizability has been measured. And it's measured with sufficient accuracy. But what's hard to measure for the experimentalists is frequency dependence of the polarizability. Because to measure that, you need a quite complicated device, and you need to measure it for very many frequencies, like 20 or 30. So you need like 20 or 30 lasers to do this measurement. So it would be quite expensive for them, and it was first challenge to get frequency dependence from theory and static polarizability from measurements. So this combined approach. And for that, to include this, this frequency dependence, we are interested in optical range of frequencies and below. So basically what you can do below the first resonance frequency is you do the Cauchy expansion. So you expand the polarizability in orders of omega, and you have the static polarizability in the first term, and then you have this Cauchy coefficients. And for argon, we did calculations of this polarizability and this first two Cauchy coefficients. And if you take a look at the static results for static polarizability, as I told you, you cannot get accuracy even comparable to experiment. It's 2 orders of magnitude more uncertainty in theory than experiment. But if you just want to take from theory this alpha 2 and alpha 4, then you can do a hybrid approach. And for example, for a frequency of helium neon laser, so this is 63 nanometers, if you use this combined hybrid approach, you can compare with what has actually been measured. And then the conclusion is you can reach 10 ppm accuracy within this hybrid approach. So this is not as good as for helium, but it's close second. The second thing for argon, which was interesting for experimentalists, is the magnetic susceptibility. I understand that it's very difficult to measure. There are only 3 measurements from 30s and 1 from the 60s, and they differ by 10 to 20%. The trick is that magnetic susceptibility of argon is 4 orders of magnitude smaller than polarizability, so the accuracy of 1% is entirely sufficient. And the accuracy of 1% is something we can easily do in theory. So again, we perform calculations using non-relativistic QED, including relativistic corrections, QED, finite nuclear mass. And in total, we get accuracy which is below 1%. So it was just trying to push as much as we can, but really this accuracy that we get is entirely sufficient from the experimental point of view. And in this case, in this particular case, they use the theoretical result instead of these experimental results from back in the day. And the last thing is the helium, is the argon density virial coefficient, second density virial coefficient. Last year, we also generated new potential for argon-2 with improved relativistic and QED components. And similarly, what you see on this graph is our result is essentially 0 here, because these are differences between theory and experiment. So theory is taken as the 0, and this pink shaded area are our uncertainties. So uncertainties of our calculations. And here, what is plotted here, all this mess, are experimental results with their error bars. So you can see that error bars are similar. So theory and experiment have similar error bars in this case. But what we managed to do is do these calculations for a wide range of temperatures in a systematic manner, estimate the uncertainty rigorously. So again, if the accuracy is comparable, they can take the theoretical result for any temperature they might want. And finally, for conclusions, first of all is that most properties of helium gas, which are useful in metrology, can now be calculated more accurately than can be measured. And this is the basis for primary pressure standards that we have today. For noble gases, we use more hybrid approach when some parts are calculated, some parts are measured, things which are difficult to measure are calculated, things which are difficult to calculate are hopefully measured. So this is like this, this combination. For neon and argon, I think we have reached capabilities of current theory, so we need some breakthrough to push by an order of magnitude, for example. And our focus now shifts to N2. We have a large project working on properties of N2. And here the problem is that we need more theory development to tackle this problem. I would like to thank my colleagues and co-workers from Warsaw, from Poznań, from Italy, and also, of course, the experimentalists who are extremely important here. So thank you very much, and also funding agencies. So thank you very much.
Thank you, Michał, for this talk, and it's open for the discussion. I see Rafał in the back and the second person just on the left.
Thanks, Michał. Super interesting. So I was wondering why you, well, I guess I know the answer, but why you can't get this accuracy of your polarizability for argon, and can you do it any better for neon? Can you get it accurately with quantum chemistry for neon, or do you also need to use this hybrid approach?
So you probably know the answer, like the number of electrons is larger. You need to...
So that's the key issue.
Yeah, it's hard to do full CI with 10 electrons, or for 2 electrons it's quite easy. But what we need to push the accuracy, like it would need a substantial breakthrough in theory, like maybe some hilarious CI, maybe some wide explicitly correlated approaches, but with current theory, with coupled cluster and this framework, I think this is the limit. Mm-hmm. And for neon, I didn't show the results for neon, but the results for neon slightly better, but not that much better.
Okay, thank you.
The second question.
So you were showing results for electric polarizability and also magnetic susceptibility for argon. Mm-hmm. So I was curious. So to reach the same level of accuracy for those two properties, do they pose the same challenge, or there's more no, or like, there is some difference to in calculations of these two properties?
Polarizability is more difficult because it's basically a second order property. You need a response to calculate the polarizability. For magnetic susceptibility, in the non-relativistic case, it's just expectation value of R squared. So susceptibility is easier, but for polarizability, we have good theory in the sense that we know the corrections and formula for the corrections of relativistic and QED and so forth. For magnetic susceptibility, I don't think that theory is available there. Like even relativistic theory of magnetic susceptibility was developed a few years back. So there's no QED theory.
Okay, but for magnetizability, you said that this is expectation value, but this is just for like closed shell, right?
Yeah,
okay.
For non-relativistic, it's just an expectation value. For closed shell, yes. Yeah.
Okay.
Okay, maybe the last short question.
Very short question on the experimental aspect of what you mentioned. So you mentioned that it's a problem because to measure with multiple frequencies because you don't have enough lasers. Mm-hmm. But I wonder if couldn't you use a frequency comb? Or is that something that's being pursued?
I asked this question to the experimentalists, and they replied, and I didn't understand.
I see. Okay.
So short question, short answer. Thank you, Michał, for this talk.